We're going to finish this section up with one more problem. Again, okay, what does this have to do with? You look at this and you just wonder, okay, what does this have to do with? Whoops. Oh, back there, I don't want that. Okay, so what does that have to do with geometric series anyway? Okay, this thing here. Whoa. Okay, what does that have to do with geometric series? And the answer is nothing at this point. Okay, we don't see it. So I'm gonna go back over to my notebook, but this arctangent of 2x, we want to center this at 0. So we need somehow we want to expand this. Okay, c equals 0. So let's come back over here and let's get in here. Okay. All right, arctangent of 2x. And we want to expand that about 0. Okay, so that's our function. And we need this about c is 0, okay? So now, this one's a little bit tricky, but let's do this. Let's find the derivative. We know that's going to be 2 over 1 plus 4x squared. Okay, now, the idea is that this now, if this were the function that I were expanding, I could do this. This I recognize as the sum of a geometric series. So I could do that, and I'm going to do that, and then I'm going to integrate it to go backwards to f of x. That's the idea. So in here we identify the a is a 2, and the r is actually a negative 2 x squared, like that. Because you know this is 2 over 1 minus negative 2x squared, like this. Yeah, negative 4x squared. Here, let's see. Like this. Okay, with a 4 in there. Okay, so you can see, in this case I wrote this 2, this is a 4, I'm sorry. Just double check my work here. Okay, so that's what r is. It's a negative 4x squared. So in my series then, and I'm going to write this in the closed form, I end up with this. I have a 2 in here, and I also have a negative 4x squared quantity to the nth power. Okay, now you might want to clean this up a bit. We could write this as, I'm going to put that 2 out in front just to leave it there for now. Maybe I'll bring it back in later, but this could be written as a 2 to the 2n and then x to the 2n, like that. And let's not forget our negative in there. We got negative 1 to the n. Okay, so it looks like it does alternate. And this is just one way to write it. Now, if you want, you can bring that 2 back in, since it's now we see it's just a 2. So one more optional step might be to bring that 2 back in. And it's now a 2 to the 2n plus 1. And we have an x to the 2n. Okay, now let's go ahead and integrate both sides of this statement. So it will be this integral of all of this. So let's see, now I'm going to integrate that term by term. I'll just stay inside on this one. -1 to the n, 2 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1. Like that. Plus a constant. Don't forget the constant. So now that is my function that I just worked with. That is the arctangent to x. Okay, because that's this left side is f of x, which is arctangent to x. Now, I don't like that c out there. I don't want to leave a constant hanging out there. So we typically will evaluate this at the center, which is 0. So we're pretty sure the arctangent of 0 is a 0. This whole thing becomes a 0 when you put an x equals 0 into it. So you get that. And that just implies that c is actually a 0. So we now have that our arctangent of 2x is all of this stuff. N equals 0. And I'll just rewrite this. All right, now, when we first started this over here, we had our r in here, and we could see that initially that we must have this. That must be less than 1, which if you work this through, you'll have 4x squared less than 1 greater than -1, and a x less than a half greater than -half. Okay, so that is our initial starting point for our interval of convergence. Okay. That means we need to check these endpoints because remember, integration usually brings about addition of endpoints, one or more, sometimes both. So we have to start with that. Let's check the endpoints. Check -1/2. We'll check that one first. So that would give us this series. -1 to the n, 2 to the n plus 1, and we would have a -1/2 to the 2n plus 1 over 2n plus 1. Okay, now the 2's cancel, you can see that, but you do have a -1 in here and -1 here, which join together as this. -1. You got 2n and an n is a 3n plus a 1. And then you have the 2n plus 1 underneath. Okay, now that looks like it might be an alternating series, and if it is, then we'd have a conditionally convergent series. I think you can recognize that. It'd be similar to the same order of magnitude of a harmonic series. So we suspect it would be convergent if this were alternating, and if we would use the alternating series test on this one to demonstrate that. But notice this, let's check these signs on here, because if this is not alternating, then it's not convergent. So check the signs. We have a 0, we would have a -1. If we had a 1, we would have 3 and 1 is 4. So that would be positive. If we had a 2, we would have 6 and 1 is 7. It does alternate. So you could check that. If you're not sure how to do that, make sure you can. Alternating series test shows that that would be conditionally convergent. Okay, so we get to add a -1/2 into this, onto this interval. Okay, so far let's I guess we could put it over here. We would have this. So far we got a -1/2 included. Question is, what are we going to do with that half? Should we include it or not? Let's check it. Check 1/2. So you have n equals 0. negative 1 to the n, 2 to the n plus 1, and you have a half to the n, 2n plus 1 over 2n plus 1. Now the halves do cancel each other here. The 2 and then this half, they are wiped out, and you have this. You have that over 2n plus 1, and I think that one is obviously the alternating series, and it does converge for the same reason that this other one did. It's going to converge conditionally, but it does converge. So you're back over here, then we can restate our new interval of convergence, which would include the half. So this is your final answer. And of course, your final result that you would have here would look like this. This is your series here that we just found. Okay, so there you go.